Hello everyone, reporting today for Fun Robotics Network. I'm Abhas, and with me here is none other than Team 16460, GEarheads from Brookfield, Wisconsin. They were 5th in the world by non-penalty OPR after their last competition in late November, and they're currently 6-0, winning Alliance Captain, Inspire Award winner, just one of the best robots I've seen so far this season, and I can't wait to talk about it coming up on this Behind the Bot. Alright, Gearheads, so I think every year you guys really shine in your ability to combine like mechanical complexity with really excellent software skills. This year is absolutely no exception. So let's start with your approach to the game in general. When you first saw Into the Deep, what were you thinking?
Yeah, so one thing we noticed is that it's really common for the yellow and the color blocks to be interspersed, so it's kind of difficult to make an active intake that's able to differentiate between them. So that's why we chose to go with a claw with a lot of degrees of freedom as our main intake mechanism. And so another thing we noticed is that in previous years where there have been game pieces scattered around a lot, it's often better to have a robot that can move its end effector to the game piece rather than moving the drivetrain all the time. So we strove to add enough degrees of freedom for the claw to be able to grab any block without the drivetrain moving.
Sure, and so on the topic of the drivetrain, just talking about that a little bit, I mean, it looks like a fairly standard Mecanum drive. Some, obviously everyone's unique. Is there anything you want to highlight with the packaging or any specific challenges you had to address there?
Yeah, so along with one of the goals that we've had this season, two of them were to improve our loop times due to the differential we're using, as well as have a low center of gravity. The best way we do that is having all 7 of the motors on the bottom of the robot. And the best way we improve our loop time is by using the SparkFun optical sensor, which allows us to improve our loop times by doing all the computing that an encoder would do normally on the control hub on the chip itself.
And so with the Otos, I think we've seen some really great results with teams on those. Do you guys have any tips on like cleaning it or maintenance? I know that's something people have been worried about. Was that something you guys have faced so far or no issues there?
For us, it's been pretty maintenance free. We would advise you to keep your field clean because the dust from that is the main cause of it not working.
Okay, yeah, awesome. So let's jump right into the active intake starting. Definitely one of the most unique features. Honestly, your whole robot has a lot of unique features, but very special in its own kind. So just walk me through the general design and then we'll get into some specific questions.
All right, so even though we are using a claw to intake in the submersible, we wanted to have an active intake to get the samples, colored samples that are on the ground and autonomous, as well as any that might be there in teleop. So we just have this small active intake that's stationary in the front of the robot, and that's driven by 2 Melonbotic super servos, and we were lucky to get those sponsored. So here's a demonstration.
Awesome, yeah. And so a couple questions there. I mean, obviously you guys have built a very robust active intake. Why did you decide not to have it on on the pitching slide system itself?
Yeah, so we found that with robots that are using intakes as their claws, one, they're fairly heavy at the end because you have to include things like the melonbotic servos as well as rollers. And we also found that they struggle, at least in our testing, with different orientations on blocks. So we thought that a simple claw design that had a lot of mobility, like Josh stated earlier, was best for this year.
Cool. And talking a little bit about the programming, I saw either just very good driving or as soon as pretty much the block, the sample is in there, your claw comes down and picks it up. Is that sensor based or current? Like, how are you doing that?
Right now we don't have a sensor on it.
Okay.
So you probably must use it in autonomous, so it's just timed. So that slightly preempts the block coming into the intake, so it gets it almost right when it comes in.
And so for teleop, when you're transferring, that's just entirely driver based or any sensors there? Okay, got it. And now talking a little bit about how this plays into the auto pathing. I mean, obviously you guys are no strangers to fast autonomous paths. Have you struggled with having to drive more in autonomous because of the active intake, or has that really not been a concern?
No, for the bucket autonomous, we found that our speed has been limited by the extension and retraction of the slides rather than driving. So we actually set it around half speed and it's perfectly fine.
Okay, awesome. Yeah, so now jumping into the slides themselves. you guys seem to have a very complex, but well-executed just outtake mechanism in general. So why don't we start with an overview and then we'll jump into specific questions.
Oh yeah, so another thing we noticed in our initial analysis of the game was we thought a lot of teams would use a separate extension and deposit mechanism that needed a transfer. And in the past, we've had some trouble with transfers and getting items stuck inside the robot when it doesn't go right. So we decided to have a transferless system with pivoting slides, as you can see here. So yeah, so this yeah, so the pivot is driven by 177 RPM motor, and the extension is two bear motors that are on a 5-to-1 belt ratio with a 36 millimeter spool. And we found that's able to reach pretty close to the free speed, and it's fast enough for our needs.
Awesome. Yeah. So talking about the extension itself, I think I see you guys are using linear rails. Are those MGN9s or?
Oh yeah, these are MGN9 linear rails.
Mm-hmm.
So we originally used these because we couldn't find 350 millimeter drawer slides, and we would have to use 4 of the 300 millimeter ones. But we found these are better than slides in some ways. For instance, we can make the first stage longer than all of the other ones, and because all of the weight, the only moving weight is the carriage, this saves effectively 2/3 of the weight. And also, although it's not very rigid in this direction, you can sort of bend it like that. It is very rigid in the up and down movement, which is what we need for both the deposit and the hang.
Awesome. And have you guys had any need to counter spring it or do anything like that?
Oh no, it isn't counter sprung right now.
Okay.
Just the deposit light enough, we didn't need to.
Yeah, and I think I heard you also mention a differential. So you're saying that's not with your slides, but rather later in your end effector, or is that with your slides?
Oh yeah, so it is on the slides. So let's show that with the specimen position.
So the differential controls are vertical up and down or out and in case of the submersible, as well as the rotational movement of the claw.
Okay, wow. I see. And so is this mechanism, like, is it heavily based on like previous differentials you've built like in last year and things like that, or was it just completely different from those?
I would say it's fairly similar to previous differentials. So the other 2 differentials we worked on included belts, but this one is our first string-driven differential drive. And for this one, when the motors rotate in the same rotational direction, it'll actually it'll rotate the string along, and it'll actually rotate the slot around. When they rotate oppositely, then it'll lift it up and down.
Yeah, it's pretty similar to last year you saw in Behind the Bot. We had the up as well as left to right motion with the pixels, but for this year it's better to have the up and the rotational motion on that turret.
Okay, got it. Yeah, and so now talking about that rotational motion, how you're moving it around, do you use that, how do you use that throughout the match?
Yeah, so the rotational motion you'll see is highlighted in our autonomous the most when we do specimens like this. And what it allows us to do is make the drive path essentially a line back and forth, and the turret and the claw will do all of the angling that the drivers need to do. So essentially the drivers will drive back and forth in a line, and the robot does all the angles to pick up as well as put on the bar.
Yeah, that's fantastic. And so now talking about your claw a bit, I think the packaging there with the 3 servos is just really excellent. It's very impressive. And so can you walk through kind of the actuators you're using for your claw, and then we'll talk about the claw itself.
Oh yeah, so first for the main motions of the claw, you can see we've got it on this little bevel gear differential here. And what that lets us do is control the actuation, so we can grab blocks at all angles. And this is field oriented, so the driver will select the orientation of the block that they see before they go into the submersible, and that allows us to improve our cycle times in teleop. And later, in concert with the differential movement, we hope to be able to grab blocks in autonomous without having to turn the drivetrain at all. So that's what this blue mount is for a camera later.
I see. Okay. And yeah, just talking. So if we shift back just a little bit from your claw down to your turret base where you have like the 3 servos positioned, can you walk through exactly what those servos are used for?
Yeah, so first you can see we've got all these servos packaged flat in here, and that helps us keep our robot height down. So what these two servos on the side do is they control the differential movements of the claw. And actually the claw's axle is from two live axles from these two servos, along with this supporting block in the middle. So that was a packaging choice we made to keep everything compact. And also this, the arm movement is driven by one servo on a linkage. And we found that linkages are better in terms of backlash, especially when you have a linkage bar with ball bearings in it. So that was part of our decision.
I see. And so with that linkage, you can't get that full 180 degrees range of motion. Is that a problem for you guys, or has it really never been a concern?
We haven't had a concern. So the wrist, as you can tell, has about 270 degrees of freedom to turn. So that allows us to drop in the bucket as well as pick up without changing the robot heading. As well as if we had issues with the vertical movement of the lift, we could also be lifting it from the back here to get a different height.
Yeah,
Sure.
with the wrist, that'll make it so that once the arm is kind of aligned with the bucket or anywhere else, generally the wrist has enough movement to be able to properly maneuver a block to wherever it needs to be scored.
Okay, and those are just carbon fiber plates on the sides for the arm?
Yeah, so we have 2 CNC mills in our workshop, and this year we learned how to machine carbon fiber. So we've featured that on the lift as a feature to reduce the weight of the lift and make the center of mass lower.
And there are some other safety concerns and also special tooling. So we've limited that to the lift for now. We've seen other teams use it on the drivetrain or other plate parts without any problems.
And so now talking a little bit, just going back to the pivoting and like the pitching of the slides. So you said that's motor driven, and is it I think I saw a linkage back there. How are you hard stopping the slides in both like the forward and like stowed and vertical positions?
No, this is a belt-driven pivot. So
Okay.
we have a 12-tooth to 48-tooth belt ratio from a 26.9 to 1 ratio motor. So that provides sufficient torque for all the movements we need. And the hard stops on both sides are just different locations on these pivot side plates here.
Okay. I think
These standoffs.
I see. And yeah, I mean that's just really incredible. Now moving on to endgame, I think hang is really the last thing we need to talk about here. How do you hang?
Yeah, so we also wanted to keep the extra parts needed for a hang to a minimum. So because we have all of these degrees of freedom on the pivoting slides, we wanted to use that for hang. So you can see we put one pair of stationary hooks on the end of the slides, and also this pair of 2 hooks on the body of the pivot. And these hooks are pivoted on a spring. So what this allows us to do is bring it down, and then the bar will spring into position. So we had enough torque on the pivot to accomplish this, but because we wanted our slides to be as fast as possible, they didn't have enough force to lift the robot. So this year we've included a power takeoff to the 4 drivetrain motors. So if you turn over the robot, you would see 4 gears, 1 on each of the motor shafts. And then we have a servo-driven linkage that locks a gear into each of these 2 pairs. And that allows us to have all 4 drivetrain motors powering the hang. And that allows us to be still pretty fast without any extra complexity here.
Wow, yeah. Is it possible to turn the robot over and take a look at that underside?
Yeah,
It's
quite pretty hard to see.
Yeah, it's
Okay.
pretty far into the spot.
But there's a servo with a linkage that comes between these 2 black gears driven on the drivetrain motors.
Okay.
And that engages the 4 drivetrain motors as well as the 2 lift motors. So we have 6 of the motors lifting the robot up at once.
Okay.
Which makes the time and the reliability much better.
Wow. And so with that, have you guys looked at the current draw during these operations and, just seeing like how much current you're pulling, or has that just not been a concern?
So we designed this to be at around peak power. So I think that's around 15 amps expected. So that is a little close to the fuse capacity, but we haven't had any issues yet. Well, when we tried to do the level 3 hang, we did have a blown fuse. So that will be an issue we have to investigate. And while we're on that topic, so we accomplished the level 3 hang using this, hold it up. Using this passively driven mechanism.
Oh, wow.
So these feet here catch under the bar, so they allow us to keep our robot position steady from swinging. And once we latch onto the level 3 bar, that'll retract back with springs. And these are MGM7 Lily rails here.
Wow, that's just really incredible. Gearheads, thank you so much. I mean, this has just been one of the best robots I've seen this season. I'm so glad we could do this interview. Looking forward, you guys said you're competing next week. What changes would you like to make to this robot? I know you mentioned the camera and speeding up that level 3 hang. Anything else?
Yeah, so adding the level 3 hang, as well as we're testing different strings for reliability. So we're torquing on the springs, or the string really heavily when we're lifting, especially at the end game, or lifting blocks really quickly. So we've been testing around with different strings just to see which string type is best.
And right now, what are you using?
We're using a polyethylene string. This is 0.8 millimeter diameter, so it's around 100-pound capacity. And we found that to keep its tension pretty well once it gets past the initial stretch.
Okay.
We did test around with other Kevlar strings with a higher weight capacity, but those broke after stretching a little bit, and they don't stretch as much.
I see. Okay, yeah, Gearheads, thank you so much. I mean, this robot's just incredible. I really hope we get to see it compete at the World Championship, MTI, I mean, just all the premier competitions, because it's just going to be amazing. So thank you so much for reporting for Fun Robotics Network. I'm Abhas, and this is Team 16460 Gearheads from Wisconsin.